안녕하세요. 저 뒤에 문 좀 닫아줄래요? Okay, let me first introduce our TAs. Our head TA is Shihun Chu, and this is Junsu Byun. I'll introduce them first, so they can leave. Right. Do you have any advice for students?
I have nothing to advise. Thank you. You can, we're gonna make open chat, so I think you can ask if you guys have any questions.
In my opinion, it was the most interesting course that I took when I was undergraduate, so I think you can gain more if you do your best, so I wish you luck.
All right, so let's begin. This is Introduction to Deep Learning, and historically, many students from many other departments and different stages in their career take this class. How many of you are freshmen? No one? Okay, how about junior, second year? Okay, typically second year students, they all get high grades. I don't know why. Right, and logistics. So if you're from these departments or interdisciplinary course, you can take this class. Otherwise, I'm sorry, but you cannot, because we have limited GPU resources. So in case you don't read Korean, if you're from STAT, Math, CS, EE, or how do I translate this? College of Liberal Arts? Is this how you read it? Or did I miss something? So I think this is not updated, but if you're also from College of Medicine, you can take this class as well. How many of you are from College of Medicine? Okay, 3, 4. By the way, I founded a startup in healthcare, specifically in intensive care. So it's great to see students from College of Medicine take the class. I think in the future, near future, one of the most important skills for doctors is being adept in AI. Okay, so we introduced Shihun and Junsu. They're going to be lead TAs, and we have other 3 helping TAs to help with grading homeworks and exams. And there's no official textbook for this class, mainly because the class material changes a lot over the years. And what are the prerequisites? So you're expected to have taken courses in linear algebra and calculus, probability theory as prerequisite. And if you have never taken classes among these, then you can do a self-study. It's not very difficult. One of the things so before becoming a professor here, I used to work at Google Research, now Google DeepMind, as an AI researcher. And one of the things I learned at Google is don't try to learn everything. So just keep doing what you are trying to do. And important thing is, if you don't know something, only then try to study it. Because there are so many things to study, and especially in CS, things keep changing. So if you master one of the prerequisites, then it may no longer be relevant. So try to focus on your primary task, and if you encounter something that you're not familiar with, and then study just that portion. I know this may seem counterintuitive to students who's just out of high school, but this is just how it is. There are so many things to learn, and things are changing really fast. So don't get discouraged if you have never taken classes here in linear algebra, calculus, probability theory. You can, if you're really motivated, you can teach yourself. And I recommend you to use ChatGPT or Gemini to ask questions there. And I use these LLMs to learn new concepts as well. It's much faster to learn with LLMs than, go to a Wikipedia page and try to learn everything. Yeah, so you can ask questions on bulletin board on ETL, or post questions on our Kakao chat room. And grading, we're going to post the template file for the homework. So it's going to be a LaTeX file, and you're supposed to do electronic submission only. So you're only supposed to submit the PDF file generated from the LaTeX template. And you cannot use Microsoft Word or Hangul or whatever you're supposed to use this. And it's very useful to learn how to use LaTeX, especially if you're ever gonna write a paper, either in medicine or electrical engineering, math, CS, stats, whatever. Okay, and here the grades are going to be homework, participation, project, or midterm. We haven't really figured out if we want to do a project this year. We haven't decided yet. Last year we did, and we had some mixed reviews. And there's going to be definitely a final exam that covers everything end to end, from lecture 1 until the last lecture. Covers everything in closed book. And the homework, no late submissions are going to be accepted, and there's no exception. So what we're going to do is we're going to omit one homework, your lowest homework score, and then take average. So you have a chance to utilize this if you want. So if you have some excuses like doctor's notes, conference travel invitations, don't send them to me, because we're going to stick to this rule. So we're going to take your lowest grade out once. Okay? And guys, don't worry too much about the grades. This is supposed to be fourth year elective, so I'm going to be very easy on the final grade. So the purpose of this class is to learn the inner workings and principles of modern AI techniques. If I was teaching major elective, and I would be forced to, curve you. But here, this is just minor elective, so don't worry too much about the grades. Okay, so and I encourage you to collaborate on homeworks and forming discussion groups if you want. I really encourage it. But however, you should write your own problems. So for homework, you cannot just literally copy paste your friends or peer groups' solutions. Okay, any administrative questions before we proceed? Oh, and by the way, we're gonna record the lectures, and it's gonna be made available on my YouTube channel. Today, I removed all my old videos from my YouTube channel, if you have ever looked at it. Yeah, you have a question?
When will you decide to do project on YouTube?
Very soon. Within March. Yeah. Any other questions? Oh, so the question was, when will I decide whether we're going to do project or midterm? Yes? Yeah, you can ask in Korean. We are recording live. Yeah. It's going to be made available on YouTube, so you can watch it anytime. Yeah. Any other questions? Okay. Yeah, so like I said, the goal of the class is to provide grounding in algorithms, mathematics, theory, and underlying intuition to be ready to do in-depth research and applications in AI. And since last year, we removed a lot of the optimization related lectures, condensed it in 1 or 2 lectures, and instead we have about 3 weeks dedicated to do hands-on LLM building, which I think is going to be very useful. So we're going to all going to be using Google Colab, and we'll soon post instructions on how to set up Colab. And there we're going to start building LLMs, starting from tokenizer, positional encoding, and building one transformer block and stacking it up, and multiple heads and extensions. Okay, so let's do some basics. So what do people really mean when they say machine learning? So it's a series of algorithms that learn from data. So X is your data, Y is some output, and you're passing it through some function. So this function is the algorithm that we're referring to. And there are many different categories in machine learning, and perhaps you're most familiar with supervised learning. So for example, you plug in some image, of a cat to some function, and it's supposed to output among a predefined set of categories. Cat, dog, person is supposed to output some probability distribution. Which corresponds to its prediction on the label associated with the input image. So this is, I guess, one of the most applied version of machine learning. So to do this, you will first have to curate a data set, which is a set of tuples, xi, yi, where x is a set of images, y is, for example, in this case, its corresponding class IDs. K is number of classes. So when people say binary or multi-class classification, it just means binary means k is equal to 2, multi-class means k is greater than or equal to 2. How many classes? And regression, the difference is that here the label space was discrete, choosing one category out of a list. Here, the label space y is RD. For example, you plug in I don't know, a photo of a shoe, and you're supposed to predict the size of the shoe or something like this. And you're not restricted to inputting one data. You can actually insert a sequence of data and also output a sequence of data. So one application here would be language translation. You input sequence of n words, and you're supposed to output its corresponding translation in another language. This is all supervised because during training, you're providing these mapping, X to Y mapping. And prediction, you're given some sequence Y, and you're trying to predict the sequence in the next time step, given some additional information. So for example, this could be a stock prediction. So you're trying to provide T-1 inputs of past market close price and some information about the current state. And you're trying to predict the stock price for the next day. Okay, so I gave you an example of multi-class classification in the computer vision domain. You're given some image, and the function f is trying to predict the probability distribution on the class labels. And actually, for us humans, this is naturally a cat image. It's very natural. But in terms of computer, what it sees is this three-dimensional tensor. So I guess to make the correspondence to this image, this has to be height, width, and channel. 3 channels for the color image, red, green, blue. So computer sees array of these numbers, So for example, for uint 8 image, each number here is going to be an integer from 0 to 255. So for the computer, this is extremely difficult problem. So when I learned this in graduate school, professors will typically make analogy to human systems. So I'm not an expert on human vision, but just to give you some analogy, so you have your eyeballs here and your brain, and brain is layered in multiple layers of visual processing. So here you have visual cortex, and it's layered V1, V2, V3, and what the scientists done back in the day was, I think it was monkey, or it was cat. So they took the cat and they stick in some needles here, and they observed that V1 is very sensitive to these type of edges. So if you show these edge images, then you have huge spikes here. And then for V2, these are more part-like. So if you insert, I don't know, some round object, some rectangular object, or a fragment of a circle, something like this, then you get high spikes in V2, and so on. And V3, it's more sensitive to higher level concepts. So I don't know, now this is a wheel, or this is a part of a person, or something like this. So you have this layer of sensitivity from your visual cortex, starting from the eyeball. This is sensitive to edges and sharp contrast in color. This is sensitive to these early level images. This is sensitive to a higher level context. So this is going to be very analogous to how we build convolutional neural networks. Okay, so we talked about supervised learning, and how about unsupervised? So most well-known example would be clustering. So you're given a set of data, and you're supposed to find clusters that represent these data points. So for example, in 2D, if you project the data points in 2D space, and if data are well clustered, then if you run algorithms such as k-means, it's going to identify these centroids such that distance. So what you're gonna do in k-means is you're gonna compute. You're gonna make a correspondence from each data point to its nearest centroid, and then measure the distance to the centroid it's assigned to, and sum up these the blue edges. That's going to be your cost function. So the output is these centroids and their assignment to the nearest centroid. That's going to be output of k-means clustering. There's a variant called k-medoid, where in k-means, these centroids necessarily don't have to be the data points. It can be an average of these clusters. But in k-medoid, it has to be one of the data points. And typically they use MSE in the objective, and here they use MAE in the objective. And sequence analysis, you're trying to do some probabilistic reasoning. So, for example, let's say you have X and Y is, just to give you a concrete example, 1 or 0, and YT means, so you are a prisoner locked behind the cell, and you're seeing the warden, and this is 1 or 0 based on whether the warden for that day carried an umbrella to the cell. And here you're trying to infer whether it rained outside or not rain outside, because you're trapped in a cell and you don't have a window, so you cannot really observe directly whether it's raining outside or not. So here, okay, let's make it really concrete. Umbrella, not umbrella. So let's say you make some observations. It's optional whether you make observations. So let's say you observe these two days. The warden brought umbrella to the work, and here you are trying to reason whether it rained or not. Something like this. And to make it completely unsupervised, then you'll basically not observe whether, the warden brought umbrella to the work or not. Here you're trying to just estimate the probability of individual different instantiations. And independent components and dictionary learning. I think this is a little bit more detail, but you're trying to do something like this. So here you're given lots of data points, X, and you're trying to identify prototypical representations or representative data among them. So let's say you're given a lot of X's. So this data, you're given lots of them. And what you're trying to do is try to represent the data given some dictionary you're going to learn. So Xi is in D-dimensional space. And alpha I. Alpha is some sparse activation. So let's say this D is D by P, and alpha is P by 1. So you're given lots and lots of data points, and you're trying to learn this dictionary and alphas that best represent the data X. But typically, you don't want to learn any dictionary or any activation. You typically want to enforce the alphas to be very sparse. So I think we will come back to this later, but if you add a regularizer with L1 norm, this encourages sparsity of the corresponding vector. Novelty detection, you're only given axis, and you're trying to find some outlier. So outlier meaning some of the axes might be way off. So for example, in this, if I have a data point, say, I don't know, here, then it's very distant from our other data points. So how do you automatically identify these outliers? That's what novelty detection is. Okay, so independent component analysis and sparse dictionary learning. If you want to know more, you can just read the blog. But just to give you some high-level information, let's say you're given a sound wave file, and it has many different sound sources. So some of them is a siren from police car, many different people talking and music playing. Can you automatically separate these into multiple sound wave files given a single wave file? All unsupervised. And normalized cuts is an example of clustering. So I gave you an intuitive example in 2D, but you can do this in higher dimensions. So this could be, if we were to apply this in computer vision, I'm not saying this is the best way. We've had multiple axes. So this could be X location. This could be Y location. And the X3 could be color, something like this. And project your data, your pixels, the image, in these high dimensional space, where space is defined by X location, Y location, color. And if you have a pre-trained classifier, you could do something like this as well. Probability, the pixel belongs to different objects. P human, P sky, P tree, something like this. And then run k-means clustering there. K-means is not going to be optimal for computer vision, but this is one way to do this. Because k-means is not optimal here because you want spatially similar objects to belong to similar segmentation index or segmentation ID. So, and you want each these classes to be not fragmented. You want to have clusters that's substantially large enough. You don't want to have like 3-pixel cluster or something like this. So that's what normalized cuts do. It formulates an NP-hard problem. Okay, and PCA. So here, let's say you're given 2-dimensional data. You're trying to find these axes that best captures the maximum variance of the data points. So you can do dimensionality reduction as well. So let's say you have identified first principal component, second principal component, and you could just omit this and represent the data not in terms of temperature and pressure, but in terms of the coordinate along the V1 axis. This could be dimension reduction of 1, because we are jumping from 2D representation to 1D representation. Okay, and so far we've been dealing with static AI, but it doesn't have to be. So you could imagine this scenario where in this setting, For example, let's go back to our computer vision task. Here, you input some image and it outputs some class label or probability associated with the class labels, and it's done. It terminates. Has no consequence. But for example, in reinforcement learning, you always have consequences. So if you make a mistake here, or if you do something well, you get rewarded with positive reward, or you get penalized with negative reward. So for example, if you are driving, then you're constantly making decisions on whether to turn, accelerate, stop, things like this. And if you do something well, then you get to the goal very fast. If you make lots of mistakes, you might jump off a cliff or something like this, right? You get penalized. And if you drive suboptimally, you may, I don't know, get stopped by a police officer, and then it's going to burn about half an hour on your day of work. And you have these constant decision making and constant feedback in terms of reward and the next state. So there are many variants, and the most general form is a reinforcement learning. And to look at the figure, here you have the agent, RL agent, which is parameterized by some neural network theta, and you have your environment. This is typically black box. And the agent is currently in some state ST, and it executes an action. So the goal of the policy or the agent is to determine the best course of action given the current state. That's all it wants to do, in a way that it not only looks at the immediate reward, but in a way that it maximizes some of the reward in the next sequence of rewards until the end, if end exists. If not, some of the discounted all future rewards. So if you execute an action, environment decides which reward you're going to get and what your next state is going to be. Similarly, say you're playing League of Legends, you're observing some image state, and you execute some action. It could be pressing QWER or mouse clicks. And the environment is composed of the game engine and other players, which you have no control over. And it gives you a reward. This could be your KDA or whether you won the game. And you're going to receive a next image state. It repeats until the game ends. So depending on the episode, on the problem, there may or may not be a terminal state. For League of Legends, there's clearly an ending, but there are many never-ending environments as well. So in that case, you typically want to discount your sum of rewards so that it doesn't explode. And discount encourages, it prefers rewards that's immediate versus rewards that come after. This is exactly the compound sum of the returns in economy. Okay, so for example, for robot locomotion, how would you write down the RL problem here? So objective could be make the robot move forward and don't fall over. And state could be angle and position of the joints. And action could be the torques applied on the joints. So joint, when I mean by joint, here you have motors installed, which can output some torques that you will command. This is your action for all the joints. Reward could be +1 reward each time it's stepping upright and moving forward. And you want to make the sum of the reward as much as possible. So what is, given the current state, what is the action that you think has highest sum of the rewards? That's what the policy or the agent decides. And for playing computer games, you receive raw pixel image state, and actions could be arrow keys or QWER in League of Legends, things like this. And for playing classic games like Go, objective is very sparse. Here the objective is to win the game. And typically, you won't be receiving rewards at every time step. So you'll be receiving very sparse rewards. And it makes the problem much more difficult because let's take it to the extreme. So you have +1 if you won, -1 if you lost. So you only receive reward only when the game ends, and you receive 0 reward throughout. Then it becomes very challenging because let's say you execute some actions. So action is where to put the stone, and you are making sequence of actions, but you're all receiving 0 reward until the game ends. So it becomes really challenging to segment out which sequence of actions made the state really bad versus really good. Because you have combination of these sequence of actions throughout the game, and it becomes nearly untraceable which ones were good or bad. Okay, another categorization is discriminative method versus generative method. So discriminative method, typically in supervised learning, try to estimate the probability of label given data. Directly. And for supervised tasks, it leads to better convergence and simpler solutions. And when I was in graduate school, this was the dominant method because people were working on things that worked, which means supervised learning. It worked. So if you do discriminative method, which estimates the probability labels with given lots of supervised data, it used to work very well. And generative methods were really hard and didn't really work until, say, 5 years ago. So at the end of the day, what you want to do is you want to estimate the joint distribution of the label and the data. If you have the joint, you can normalize it to compute the probability distribution of the label given the data. So this is indirect in a sense that you need to model the joint as opposed to modeling this distribution directly. And one side effect, what people thought side effect, you can learn this in generative method, it's P of X. So if you have the probability of the data, let's say you have this crazy looking distribution and this is your X, you could sample from them. I guess high density here. And we're going to talk about various methods for generative, starting with variational autoencoders, GANs, diffusion models, flow matching, and etc. So in discriminative methods, you only care about the class conditional distribution. And so for example, here, if you have two classes, so this is class 1 and class 2, can you find the linear separating boundary If it's above the boundary, you output class green. If it's below the boundary, you output class red. Can you fit this linear line that separates the two classes? That's what it's doing. If it's not separable linearly, then you have two other ways. One is to use kernels. Which we're not going to cover in this lecture. Or you can expand your feature representation. So this is currently 2D representation of the data. So you could think about smart ways to increase other dimensions to represent the data. So in higher dimensions, it's more likely to separate the data. Unless you have a labeling error. Labeling error meaning human made an error, and for nearly identical stuff, color this red. In feature dimension, whatever you do, this is never separates. So here you're screwed. Okay, so if you have generative method and you can model the data distribution, you can do very interesting stuff. You can generate data, and you can provide some text and make it fill part of the image, or generate a voice of one person given some training data or context data of the person speaking other things, and generate language, image, music, pretty much everything. So this really didn't really work back in the days, but I think, sadly, I don't think the algorithm is very different. But more important thing was downloading the whole internet and then using lots and lots of high-performance GPUs to train a really, really, really large model that has seen everything that's available on the web. That was the key things that made the generative method work. Not really a fancy algorithm, which is very sad for me. But I think that's the determining factor. Download the whole internet. Use lots of 800 GPUs on a cluster and train it. All right, so we used to teach this in 3 to 5 weeks, but we compressed it in, I think, 2 lectures. So it's very condensed. We had to make a room to cover hands-on tutorial where you guys build LLMs. So yeah. So why we're doing this? Because almost all problems in ML can be formulated as an optimization problem. So what's an optimization problem formally? So you have multiple components, and you need to learn these keywords so that we can communicate more effectively. So a vector x is optimization variable. It's typically written under minimize. And this function f is called the objective function. It takes n-dimensional real vector and outputs a real scalar. And we're not going to cover complex numbers for this class. It's often unnecessary. And this function next to subject to is called constraint function. If you pass your optimization variable to some function hi, has to be less than some number bi, and you have m such constraint functions. And when I put a star here, this vector is called the minimizer or solution of the problem. The solution that has smallest objective value among all vectors within the domain that satisfy all the constraints. So in order for us to communicate and for you guys to be ready to read ML papers, you need to be familiar with these terms. Okay, and global minimum versus local minimum. So a real value function f defined on some domain has global minimum at x star if the function value evaluated at x star is less than function value of x for all x within the domain. In other words, has the smallest value. That's definition of global minimum. How about local minimum? So a real value function f has a local minimum at x star if there exists some strictly positive epsilon such that f of x star is less than f of x, not for all x in the domain, but set of x within the epsilon ball of x star. So this B notation is set of x's where distance between x and x star is less than epsilon. So very locally, if it's the smallest guy around, then it's a local minimum. So for example, if we have this type of function over 1D, global minimum is here, and this guy and this guy are both local minimum. Okay, so let's do a very, very simple intuitive example. So we have this parabola upside down, and we have set of constraints. We have 3 constraints. Okay. And, oops, sorry. What is the minimum? What is the minimizer? So let's first see. So we have constraint 1. Okay. X has to be less than 1. Constraint 2, constraint 3, x has to be roughly here. So it has to satisfy all these constraints. So what is the feasible set? Meaning what is the set of x that satisfy all the constraints? Yes? Yeah. Can you be more specific? He said intersection. Okay. So what is the x that satisfies all the constraints and has the least function objective value? What is a minimizer? Yes. Yes. Yeah. So this guy has the minimum value and satisfies all the constraints. So minimizer, x star is 1, and the minimum value, which is the function value evaluated at the minimizer, is 3. And you're going to hear this a lot as well. So constrained versus unconstrained minimization. So let's assume f is differentiable and assume the optimal value is attained. And the task in unconstrained optimization is to produce a sequence of points within the domain such that these sequence approach the minimizer as this iteration goes to infinity. So what is the algorithm that generates these sequence of axes that evolve into the minimizer? That's the optimization algorithm. And task is to produce these sequence of points. So this is the descent method. I'm sure some of you have heard about gradient descent, right? But the thing is, it doesn't have to be gradient. So if you take my graduate machine learning class, which I have not taught in I don't know 2 years now, but there are more advanced descent algorithms that use accelerated gradients or Hessian or other things. Doesn't have to be gradient, but it makes sense to use gradient. And here in descent methods, this is the algorithm. You want to find, given some current point called iterate, you want to find the next xk plus 1, where you take the current guy, multiply by some scalar and some vector delta x, such that your next point, the function value decreases compared to the current one. Right? You want to make progress, meaning your objective value decreased. So what is some candidate for delta x that makes this happen? So let's do a first order approximation of the function at x. So function value of x plus some constant multiplied by delta x. First order approximation is f of x, the current point, some scalar, and inner product between the gradient and delta x for small t. That's the first order approximation. And now we're going to think, okay, so what is the delta x that has this property? If you take a step in that direction, your function value decreases. So geometrically, we want this to be, okay, so we want this to be negative for sure, right? In order to make the progress, right? This has to be negative. And geometrically, we have two vectors inner product less than 0. So that implies the angle between them has to be greater than 90 degrees. So any direction that makes an obtuse angle with the gradient of the function evaluated at the current point x decreases the function. So it can be anything that forms an obtuse angle. Okay? So the descent condition is that it's a direction where the inner product with the gradient is less than 0. As long as that's satisfied, we can produce the next data point where the function value is smaller than current point. And all delta x that satisfies this descent condition is called a descent direction. Okay, another keyword for sufficiently small delta, a small step size t. So how do you find this step size, which is sufficiently small, but it also has to, make the objective function smaller than the current point? Typically, you do a backtracking search in one dimension. So just to give you a pictorial illustration on why this might be necessary, let's say you're minimizing this parabola and you're currently at here. Your descent direction, so this is a 1D problem. Which direction is the descent direction? Right, so you need to go left, but here's your gradient. But if you go too much, so let's say your step size is, I don't know, like 100, then you might just go too much here and be here. So you took descent in the correct direction, but you took too much step. So then you can multiply by some small number and keep reducing the step size until you make some progress. So I'll explain why, but the most famous or most the direction that makes most sense here is actually the negative gradient direction. So set the descent direction to the negative of the gradient evaluated at the current point. So here's the algorithm. You start somewhere within the domain, set the descent direction to negative of the gradient. You choose a step size and take a step. So update your current operating point and repeat. Recompute the gradient, multiply by -1, take a step in that direction and repeat. And when do you stop? That's an important question as well, and there are so many different choices. In unconstrained method, one of the method you can do is you can check the L2 norm, the gradient, and check if it's sufficiently small. Because in unconstrained method, at your minimum, your gradient is going to be flat. If you're curious why, try to prove it yourself. So what is the definition of global minimum? It's a point x star that's less than or equal to all x within the domain. So this can happen if and only if gradient is a zero vector. Try to prove it yourself. So this can be used as a stopping criterion. All right, so you may ask why this is the sensible thing to do. Why take the descent in the negative gradient direction? So from high school, you might have learned directional derivative, or in Calculus 1 class. So what is the definition of directional derivative? So it's the rate of change of a function at a point along a unit vector v pointing in some direction. The directional derivative is a limit of x in direction v. So the question is, what is the direction, to be specific, descent direction of the steepest descent, meaning the largest descent in f evaluated in x? It can be translated to for which unit vector v directional derivative, for which direction v the directional derivative is minimized. So rate of change of function is minimized. So it can be proven that f is differentiable at x. If f is differentiable at x, the limit evaluates to the inner product of f, inner product of the gradient of f, and the direction v. So this limit for differentiable f is inner product between the gradient and the vector v. So to expand on that, we can rewrite the inner product as norm of gradient, norm of the vector, and cosine of the angle between them. And v is a unit vector, so this vanishes to 1. So here, by property of cosine, achieves minimum value of -1 when this vector v and the gradient is pointing in the opposite direction. So the minimum value of the directional derivative is actually negative. So this becomes -1. So it's actually negative of the norm of the gradient, and it's achieved when the vector points in negative gradient direction. So just take a step back. Here, it makes sense to use negative gradient as the descent direction because it has the steepest rate of change along that direction. But doesn't have to be. It can be anything as long as it satisfies this descent condition. As long as we can guarantee to make progress, doesn't have to be negative gradient. Okay, so let's see how many slides. Yeah, I think we're going to come back to SGD later, so I'm going to skip this for now. And here's the tentative agenda. So before we get started on LLMs, we need to learn these things first. So computation graph, backprop, CNN, and issues in training neural networks like initialization, like Xavier, Hall initialization, things like this, and RNN transformers. And then we can get started on our hands-on building transformers from scratch on Colab together. And then we're going to talk about generative methods like GANs, VAEs, adversarial attacks, disentanglement. And then we're going to dedicate some time to discuss diffusion models and flow matching. And then reinforcement learning and augmentation. And this is becoming more and more important, neural network pruning and quantization. So how would you put this extremely large model so that it runs on your cell phone or some mobile device? So you need to do actually three things simultaneously. You need to prune unnecessary weights. You need to quantize floating point 16 to floating point 4 or floating point 8. And you need to do something called distillation. Unfortunately, we're not going to have time to discuss this. But you need all three to put this to so that the model maintains performance, but still is small enough so it fits in your cell phone. And you need this as well. So this is a brand new topic. And you need to compress the KB cache, which keeps stacking linearly based on your context window. Okay? All right, so that's it for today's lecture. Thanks.